Okay, let's start with the divergence theorem. So recall the divergence theorem is this. Basically, if you have a surface so a surface S, which bounds a region Q, a three-dimensional region Q, we have the following. The double integral over S of the vector field dot n ds. So in other words, the flux integral over the surface using the outward orientation equals the triple integral over the inside region, that region Q, of the divergence of F dV. Now, here's the idea. Remember the divergence of F at a particular point. That tells you how fast stuff is leaving that region. When the if we think about the vector field F as describing the velocity field for a fluid, if the divergence at a particular point x, y, z is positive, things are leaving that region. They're getting less dense there. And if the divergence is negative, then things are accumulating at that region. They're getting more dense there. So if I integrate the divergence over the inside part of this region over Q, that comes out positive if, on the whole, things are leaving the various points inside Q. If stuff's leaving points inside Q faster than it's accumulating at points inside Q, then this integral is going to be positive. This, of course, is the accumulation over all the points inside Q. Now, remember what we have on this side of the equation, the double integral of f dot n ds. This is the flux integral across the surface. Now, remember, with a closed surface, we've given it the outward orientation. So this measures how fast things are leaving the surface of my potato-shaped region here in the outwards direction. So it makes sense that these two could agree. I mean, it's plausible that they would agree. This measures how fast things are getting less dense inside, and this is how fast stuff is passing the boundary in the outwards direction. That's all the divergence theorem says. So let's try it with an example. Let's say we have the unit sphere centered at the point 1, 2, 3. So 1 out on the x-axis, 2 on the y-axis, 3 on the z-axis. So at the point 1, 2, 3, we put the unit sphere. That's a horrible sphere, but you'll have to forgive me. So the unit sphere centered right there. That's going to be my S, the boundary of that. And let's say I ask you for the flux integral. I'll give you f of x, y, z. Let me just make up a vector field here. Let's say that this is equal to just plain old x, y, z. We've seen this vector field already. This is everything sort of fleeing the origin. The farther away you are from the origin, the faster it's fleeing. And let's compute the flux integral. So find the flux integral over S of f dot n ds. We can see right away, since what we have here is that vector field that we described before, that we're going to have gas or whatever this substance is leaving this region faster than it's entering, because the far side of the sphere, things are sort of moving across it faster than they're moving into it. So we can see that this flux integral on the whole is going to be positive. Now, if we want to do this, evaluate this directly, it's quite difficult, as a matter of fact. First thing we have to do is parameterize this sphere. Now, we've already parameterized a sphere around the origin. We can move it pretty easily to get that sphere. So we can write this as R of uv equals sine u cos v plus 1 sine u sine v plus 2, and then we have cos u plus 3. And if u runs between if u runs between 0 and pi, and v runs between 0 and 2 pi, we get that sphere that I described earlier. The sphere centered at 1, 2, 3. So we know how to evaluate this thing directly. We're going to plug this in for x, this in for y, this in for z, and we have to also compute the curl, sorry, not the curl, we also have to compute the partial derivative with respect to u, and take the cross product with the partial derivative with respect to v. If we do all that, we end up with the following. We end up with sine squared u cos v, comma, sine squared u sine v, comma, sine u cos u. And then we could take that and so put this in for x, put this in for y, put this in for z. So we have the double integral where, let's say, theta runs between 0 and 2 pi, and, sorry, not theta. That does, what I meant, of course, is that v runs between 0 and 2 pi, and u runs between 0 and pi, and we plug this in for x, and this in for y, and this in for z. So sine u cos v plus 1, sine u sine v plus 2, cos u plus 3, and we'll take the dot product of that with this, sine squared u cos v sine squared u sine v sine u cos u d, let's see, the inside one was du and the outside one is dv. We could do all that. That would take quite a bit of work, but we could do it. Or we could use Stokes' theorem. We could use the divergence theorem. So the divergence theorem says that this whole thing equals the triple integral over the region inside, which we called Q. So that's the inside now of the sphere, of the divergence of x, y, z. The divergence of x, y, z is just equal to the partial of x with respect to x, the partial plus the partial of y with respect to y, plus the partial of z with respect to z. That's just going to be 3 in this case. And we can pull the 3 out. The triple integral over q, 3 times the triple integral over q of 1 dv. And since this is just the area of the sphere, and the area of the sphere is 4/3 pi, this is just 3 times 4/3 pi, and that's just 4 pi, and we're done. That's so much easier than this. So the divergence theorem is definitely your friend.